Hello everyone, welcome to day 4. Before we start, let me introduce our team, which is being coordinated by Jakob Macke. I'm Christina Savina, will be doing the introduction. Ari Benjamin, Pierre-Etienne Fiquet, and Anji Wu have been working hard putting together the materials for the tutorials, and we'll be wrapping things up with the outro presented by Ilmenning Park. A little bit about myself. I'm an assistant professor in neuroscience and data science at NYU. I run a computational lab where we develop both theoretical models and data analysis tools. Our goal is to understand how learning organizes neural circuits to do interesting computation. We also study the role that intrinsic noise plays in brain function. So what are we going to do today? The topic of today's lectures is generalized linear models, what they are and what they are good for. First, to motivate the use of such models, let's think about some common statistical problems that we try to solve in neuroscience. The first important example is that of neural coding. For instance, we record neural responses as the animal is looking at a set of stimuli, and you want to be able to say which particular features in the stimuli does this particular neuron care about. More formally, we want to be able to map any particular stimulus X into the corresponding neural responses R. In this case, neural responses are typically represented at discrete counts, corresponding to the number of spikes that the neuron emits in a small time window. The stimuli are typically multidimensional. In vision, stimuli might be a set of pixels on the screen, but depending on the brain region that we are looking at, many other options are possible. In particular, if you're looking at neural responses in a motor area, stimuli might be the position of the animal's arm. If you're recording from the hippocampus, stimuli might be the position, speed, and head direction of the animal as it's moving through an environment. A second important question in neuroscience is figuring out how the neural responses are being affecting the activity of the other neurons in the circuit. These interactions are sometimes referred to as functional connectivity. Usually they do not directly reflect concrete biophysical connections between neurons, but they can still tell us something interesting about how populations of neurons work together collectively to implement a certain function. A third important example is decoding, where given the neural responses of a set of neurons, you want to be able to predict the animal's behavior. Now, this could represent it as a binary variable. For instance, you think about the random dots motion task, where the animal needs to decide whether the dots move preferentially towards left or towards right. But it could also be a continuous variable. For instance, if you think about the brain-machine interface setup, where neural responses control directly the motion of a robotic arm. Okay, so we've seen some examples of interesting problems. What do they all have in common? In all these examples, we aim to predict a scalar output, which in the following we'll denote by y, from a set of inputs x. Okay? Generalized linear models are a particular way of modeling the map between the two. They are popular in neuroscience since they are simple, have intuitive parameters, are relatively easy to fit, and they also have some nice mathematical properties, some of which we'll discuss later in the lecture. GLMs are kind of the first thing to try before doing something more sophisticated, but they're also quite powerful in their own right, and when tweaked appropriately, they can solve a range of interesting problems in neuroscience. Okay, so what is a GLM exactly? If we open the GLM black box, we find 3 specific components. First, the linear filter, which maps this multidimensional input into a scalar output. This that gets passed through some nonlinearity, to which noise is being added to finally map into the output y. Okay. An important constraint is that the noise needs to be from an exponential family as it defines the likelihood of this model. But a lot of the other things are flexible. So this is really not a single model, but rather a family of models. Depending on the type of output, the choice of noise and nonlinearity, many particular instantiations of models in this class are possible. And these can be used to solve a range of different problems. Okay, we're going to look at some concrete examples in the following, but before we do that, let me make a quick terminological note. Despite the somewhat strange misnomer, generalized linear models are not, in fact, linear models because of the nonlinearity in the middle. So they can map relatively complex dependencies between inputs and outputs. Okay, so how are we constructing individual models from this class? The main feature that dictates the choices we make for a particular problem is the nature of the output. And we kind of work our way backwards from that. If the data is real valued, then it is natural to assume Gaussian noise. In this case, we can even skip the nonlinearity altogether by making it the identity. Putting all these three components together results in a familiar model, which is simple linear regression that you've seen yesterday. Now, if the output consists of discrete counts, then the natural noise model is the Poisson distribution. This is parameterized by one parameter called lambda that needs to be positive. This positivity constraint restricts the choice of nonlinearity, but the popular choice is to use an exponential function. These criteria together result in what is called the Poisson generalized linear model. This is probably the most commonly used in neuroscience. In fact, when people in the neuroscience community talk about the GLM and specifically, they typically mean this specific model. Okay, so the output could also be binary. In this case, the natural noise model would be a Bernoulli distribution parameterized by one parameter p. This corresponds to the probability of getting heads when tossing a biased coin. So it needs to be between 0 and 1. A good nonlinearity for this is the logistic function, which looks like this. This also gives the name of the resulting model. Okay, so for now we kept things rather abstract. Let's have a look at a couple of concrete examples. So in the first example, we're going to consider a one-dimensional input because it makes things simpler to visualize with a temporal filter. That means that responses depend on a sequence of inputs rather than only the instantaneous input. Okay. Also, for convenience, we're going to assume that the time bins for the discretization of the spikes are very small, such that we can only have 1 or 0 spikes in a time bin. Since the output is binary, that results into a Bernoulli distribution as the choice of noise model and the logistic as the choice of nonlinearity. Okay, so let's look at this in even more detail. So here we have in blue a particular trace of the stimulus. Below we have the sequence of corresponding binary outputs. The model assumes that the responses of the neuron at time t are determined by stimuli in a, say, 10 time step window before it. A temporal filter shown in red maps these neural responses into a linear output. In this particular case, this output will be a positive when the recent stimuli are above 0 and the really early stimuli are below 0. This output is then passed through this squashing nonlinearity, resulting in a probability between 0 and 1. If the output is positive, that will increase the probability of observing a spike in this particular time bin. And the same kind of things happens for any subsequent time step. Okay, so the second example that we want to look at is that of the Poisson GLM. So the distinction here that the time bins are coarser, so we can have more than one spike in a single time bin, so we need to have discrete observations. In this case, we're going to assume Poisson noise for the likelihood and the exponential linearity that maps the output of a linear filter into a positive mean firing rate. To illustrate some of the variety in terms of possible inputs and filters, here we're going to take the stimulus as a set of pixels and on the screen, and each of these pixels gets multiplied with the corresponding entry in the filter, and these weighted sum together gets passed on through the nonlinearity in order to generate the firing rate. Okay, so since I said that the Poisson GLM is the most popular version in a neuroscience context, we will look into the mathematical formulation of this model in a little bit more detail. Okay, remember that in this case, the output consists of a discrete count, and the noise is given by a Poisson distribution, which has this particular mathematical form. Now, if you haven't seen this before, this is a single parameter distribution defined for positive integers y with the parameter lambda, which in our case is given by a linear filter followed by an exponential. Okay, so here I've written this in vector form just to keep things short. Now, lambda is the single parameter of this distribution. It gives both the mean and the variance. So we can see in the right how this looks for three particular settings of lambda. So the bigger the lambda, the more symmetric the distribution. The small lambda, the more skewed the distribution. Okay, so ultimately what we want to know when fitting such a model is how well it describes our particular data. And we assess this by asking how probable is that the data that we have would have come from the model for any particular choice of model parameters, theta. So this is quantified by a quantity called the data likelihood. Typically, we assume that the noise is independent across time points t, so that this distribution factorizes. So the probability of observing the full data sequence becomes the product of the probability of observing the individual neural responses. And since the individual probabilities are numbers smaller than 1, when we take this product, the final result will be a very small number. So for numerical stability, we typically choose to represent log probabilities instead. Okay, so since the log of a product is the sum of the logs, the log likelihood becomes a sum of log probabilities for individual data points. Now, the individual probabilities are themselves a product. So each of these components would also decompose in 3 terms, of course, marked here by color. So the third term we typically take as a constant because it does not depend on the parameters. It just corresponds to the sum of the log of the factorials. Okay, so we've computed this quantity. What do we need it for? The answer is for parameter learning, where whenever we try to fit parameters to data, we do this typically by a maximum likelihood estimate, or MLE. That is, we want to find the parameters that maximize the log likelihood of the data. Okay? So in particular for the generalized linear models, this optimization has a nice mathematical form because the log likelihood is concave. So it looks something like this. That means that there exists a single global optimum at the top of this hill. Okay, the existence of a unique optimum doesn't mean that we can write this in closed form. In fact, more often than not, we need to rely on numerical optimization to find it. Because in the world of optimization, we like to minimize rather than maximize functions, it is common to do a sign flip here. And instead of maximizing the concave log likelihood, we typically minimize the convex negative log likelihood. For this, we can use an algorithm called gradient descent. We don't have time to talk about this in detail, but the easy way to visualize its behavior is as a ball going down a hill, where the 2D position in space corresponds to particular settings of the parameters theta, and the height of the hill corresponds to the negative log likelihood. Now, if we place the ball and some initial condition, gradient descent will make it fall downhill to the lowest point in the valley. Okay, this is why it's important that the negative log likelihood is convex. If the function we were optimizing had non-convex structure, there would be multiple valleys shown here. So exactly where we'd end up would depend a lot on the initial conditions. Moreover, we might not end up in the deepest of the valleys. So if we start from here, we're going to end up in a local optimum. Okay. Specifically for GLM models, we don't have to worry about such complexities, and we are guaranteed to always find the optimal solution. Now, there are some practical considerations. This is not really the end of the story. Additional things need to be sorted out when applying this procedure in practice. In particular, MLE gives us the best fit on the training data, but does it give us the best model? The answer is not necessarily. Let's consider a concrete example where we've generated data from a GLM with true parameters theta shown in black, and in red we are showing the estimated MLE parameters. Now you can notice by eye that these look quite noisy and very different from what we originally started with. And this kind of behavior can be a signature of overfitting. Now, to get better intuitions of what overfitting is about, let's consider a simple cartoon. So here we're trying to fit a set of training data shown in gray. Now, as we vary the model complexity, which we can roughly approximate by the number of parameters, our ability to fit this data will change. In particular, if the model is very simple, for instance, we have a linear model, it will have a limited ability to capture the underlying structure of the data. At the other extreme, if the model is flexible enough, it will have enough parameters that the MLE will result in a perfect fit to the data. In a way, it fits the data too well, in the sense that we not only capture the underlying structure, but also any additional noise existing in the process. What this means is that although the performance on the training data is very good, this kind of model would generalize poorly to new test data. There is an intermediate value in between these two extremes that gets the complexity just right, in the sense that it not only captures most of the structure of the training data, but it also generalizes well to new data. So at one extreme, very simple models might result in a poor fit because they don't have enough degrees of freedom to capture the two structure in the data. At the other extreme, we are doing extremely well on training data but with poor generalization. And there's a middle ground where things are just right, where we sacrifice a little bit of the performance on training, but win a lot in terms of ability to generalize on new data. Okay. So the poor generalization extreme is the overfitting that we were mentioning before. In the case of GLMs, this typically looks in extremely rugged estimated filters, where the model is in a way too flexible, so the parameters adapt too quickly to reflect quirks of the training data that do not generalize. Now, a simple solution is to add an extra term in the function that we're optimizing, which somehow encourages better behaved solutions. Here in particular, we will want to penalize large weights, because these are large fluctuations at the extremes. And we can do this, for instance, by decreasing the likelihood for theta values that have high L2 norm, okay, where the L2 norm is just a simple sum of squares. Okay. So this regularization comes with an additional hyperparameter beta, which is a free knob that needs to be set sensibly. So to get some intuitions about what beta does exactly, let's think about this cartoon where we vary systematically the magnitude of beta and look at the resulting log likelihood for the optimized solution. So the final estimated parameter is theta. Now we can do this both for the training set and for the test set. For the training set, as beta increasing, it is pushing the optimization away from the maximum of the log likelihood, right? Because of this extra term, resulting in somewhat worse scores. In a way, no other parameters it finds can possibly match the ones we get without regularization, since that corresponds to the global optimum. The interesting bit happens, however, on the test data. So at one extreme, when beta is very small, overfitting happens. So although the log likelihood on the training data is very good, the generalization ability is poor. At the other extreme, beta is so strong that it dominates the optimization. So this we're stopping to listen. We no longer listen to the data at all. This results in poor performance on both the training set and the test set. And there's a Goldilocks region in between where beta is again just right. That reasonably trades off between our ability to match the training data and our desire for simple, well-behaved solutions. Okay. Now, this particular intermediate regime is found by cross-validation, where we just try different values and pick the one that behaves best in terms of test performance. Now, beta itself is also a parameters of sorts, so optimizing hyperparameters is also prone to overfitting, the same way the optimization of parameters is prone to overfitting. So as a practical consideration, we need to set aside a special subset of the data that is dedicated exclusively for tuning the hyperparameters. Some people refer to this as the validation set. There is a little bit of terminological confusion in the community. Sometimes you might have this as the test set. Okay, so we figured out how beta works. What other choices of regularizers are there? So we've seen the example of the L2 norm, which is designed to keep the weights small. Another popular example is to use an L1 norm, where instead of doing the sum of the squares, we have the sum of the absolute values. Okay, so this is a choice that encourages sparsity, where sparsity is defined means that it favors solutions where many of the thetas are strictly zero or very, very small. Now, why would we want this? Like, we can think about the scenario where we have a really high dimensional input space, but the neuron only cares about a small subset of those features. And we don't know which of the many input features are the ones that the neuron actually cares about. Only that it's only a few of them. So in this kind of scenario, L1 is the natural choice. Now we can get a bit more intuition about the behavior of different regularizers if we know a bit of geometry. So again, more cartoons. Let's consider a two-dimensional space with axes θ1 and θ2. The gray contour lines here show the log likelihood. Now, or negative log likelihood. Now, in the absence of regularization, so where beta is 0, the optimization will bring the solution to its optimum, as we've seen before. On its own, when say beta goes to infinity, the dynamics we want to shrink towards 0. For intermediate values of the beta, we're going to have a trade-off between these two forces, with the magnitude of the beta deciding which of the two constraints we enforce more strongly. Now, let's consider the set of all possible theta parameters that share exactly the same penalty value. So in a two-dimensional space, this would be on the circle. So if we constrain the sum of the squares to a constant, you get the circle. Among all of these parameters, the optimization procedure will pick the ones that have the best possible log likelihood. So this particular point in our example. This is how we trade off between the two components. Now let's see what happens if we try to do the same thing in the case of the L1 norm. So again, we have the log likelihood just as before, but for L1, the set of points that have exactly the same penalty is no longer a circle, but rather this sort of rotated square. Okay? If we're running the optimization procedure, we're more likely to find a solution that lies along one of the axes. So that means that one or a few of the thetas are non-zero, but the other thetas are 0, which is exactly our definition of sparsity. Now, L1 and L2 are the most popular, but they're definitely not the only choices of regularization. For instance, we might want to encourage smoothness by having neighboring theta have similar values. It is also possible to combine multiple regularizers together, and the exact choice will depend on what makes sense in the context of our particular model and dataset. Okay, so we're close to wrapping up. Let's spend a couple of minutes talking about an alternative interpretation to regularization from a Bayesian perspective. So it can be shown that when you combine maximum likelihood estimation with the regularization, what you get is a maximum a posteriori estimate, and the regularizer acts as a prior. Now, it's likely that many of these words will not make sense to you at the moment. They will become a lot clearer after you have gone through the Bayesian module later down the course. So I would strongly encourage you, if you haven't seen Bayesian statistics before, to revisit this point after you have done that part of the module. But just to break it down and sort of in mathematical components, the general idea is that you can write the regularizer as yet another probability distribution. So specifically for the L1-2 norm, this term corresponds to the log of a normal distribution with zero mean and some beta-specific variance. Okay, so what does it matter? Again, we have a sum of logs, which is the same as the log of a product, where the first part corresponds to the likelihood, and the regularizer part can be interpreted as the prior. That describes what are our assumptions about probable values of the theta parameters that we have before having actually seen the data. Now, the product of the two forms a Bayesian posterior, unnormalized, and this means that the final optimization procedure is actually trying to find the peak of this posterior, which in technical terms corresponds to a maximum a posteriori estimate. Okay, so finally let's put everything together that we have learned today. Going back to our overview of the GLM framework, GLMs provide a unified framework in which you can define models that are adapted to the particular problems you want to solve. This involves specific choices for the nonlinearities and noise, paired with additional assumptions about what good solutions might look like in the form of different kinds of regularization. Now, mixing and matching models and regularizers allows us to solve a range of interesting problems in neuroscience. Among these many models, almost all rely on numerical optimization to fit the parameters, but there is one notable exception, where the solution is available in closed form. This is known under the name of rich regression, and it combines a linear Gaussian model with an L2 regularization. Okay, so again, we don't have time to derive the expression in detail. I wanted to note that the expression itself is very similar to that you derived for simple linear regression, with this additional term in the parentheses corresponding to the regularizer. Okay, in summary, GLMs are a class of models that map high-dimensional inputs into a scalar output. They combine a linear filter, a nonlinear function, and different choices of noise. Different choices result in different models that are adapted to different kinds of problems that we might want to solve. The parameter estimation is done by maximum likelihood, and because of the nice mathematical properties of GLMs, this will have a unique solution, making model fitting relatively easy. Regularization is important to avoid overfitting, and it specifies our additional assumptions that we might have about what constitutes a good solution. Overall, GLMs are kind of go-to models in neuroscience. They're the first thing to try when exploring a new data set, but they're also important building blocks for building more complex models. So a good understanding of their inner works is important for understanding more advanced models that you might encounter. And here I'm thanking you for your attention, and Jonathan Pillow and Miming Park for generously sharing materials and graphics.